here we will see the codes for the stability analysis and solving the Or-Sommerfeld, and the codes that will solve the eigenvalue problem, and it will tell us whether do we have any unstable wave in the flow or not. So to start with, we have three files. The main file is the stability main, and then there are the other function file. Those function file are the Blasius boundary layer, Blasius BL, and then OS FDM, that basically solves the Or-Sommerfeld by using the finite difference method. So starting with the stability main, we specify the number of points. For that, we are going to solve the Blasius boundary layer equation. So this n goes into this Blasius boundary layer equation, and basically it returns the u, the velocity profile, the double derivative of velocity profile, the y distribution, and the dy, that y spacing. And going into the Blasius boundary layer equation, we can see that it is a function and it takes the information of n, and then it basically uses the Runge-Kutta to solve this Blasius equation, which has been set here as a function. So f1, f2, f3, these are that we've seen in the Blasius boundary layer equation as a f prime, f double prime, something like that. And we solve this equation over here, and it returns the u, and u and derivative of second derivative of u, that goes into this stability main. And here the figure 1 is going to plot the velocity profile, the mean velocity profile that we are going to feed into the stability solver. So before proceeding to the stability solver, here we specify the alpha, which is for which wave number we want to solve. Since we are doing the temporal stability, so we need to specify the alpha, and then r is the Reynolds number. So this information goes into the OS FDM, which is the solver for Or-Sommerfeld. So it takes the information of velocity, second derivative of velocity, spacing, dy spacing, r, which is the Reynolds number, and alpha, which is streamwise wave number, and n, the number of grid point. So it takes this information and it returns the c and v. So c is basically eigenvalue and v is an eigenvector. So let's go into the OS FDM and just check. So this is this takes this information, as we seen in the when we was discussing the literature. We seen in past lecture, we seen that we set the matrices variable like E, C, A, B, D, and those will be arranged in this form like a pentadiagonal matrix, and that is what is being done here. So yeah, we are creating the A matrix and B matrix, so A empty, B empty, and that we are so this is here the B cap, A cap, C cap that we seen on the right hand side of the eigenvalue problem. And then we have the AMT and BMT. So AMT is the A tilde, BMT is the B tilde, and it returns over here is the V and EI. EI is the eigenvalue that goes into the C, and V is the eigenvector. And that returns over here in this, and then we plot the real part, imaginary part of the eigenvalue distribution to check that whether we have any unstable eigenvalue or not. So let's go and run this code to see that what we are getting out of it. So I have placed, yeah, so I will run the code, and it brings up this two plot. So we have this mean profile for this particular boundary layer that we are feeding into the linear stability solver, the Or-Sommerfeld solver, and then it is giving the eigenvalue distribution. So we can see that there are many many eigenvalue, as you can go and check this, what is its real part and imaginary part. And you can see that there are the eigenvalue that is very continuous. So these are called the continuous spectrum of eigenvalue, and then we have some discrete eigenvalue over here is standing apart from this continuous spectrum. So this discrete part is very important to observe because this is the discrete part that leads to instability in the flow. Sometimes there is also some spurious eigenvalue in this discrete part, so we have to also be careful about that. So we see here that most all the eigenvalue are stable, but there is one eigenvalue which is unstable. We can see that it have the positive imaginary part, which is the y. You are seeing here y as a positive, but for most of this the y is negative. So we have one unstable eigenvalue, and this is the eigenvalue documented in the literature as Tollyman's listing wave. So now we have this unstable eigenvalue, and this unstable eigenvalue that we got is for this particular alpha and this particular Reynolds number. And if we want to get the entire picture, we can sweep through the different through a range of alpha starting from here to here, and sweep through the different Reynolds number to get the entire picture. So once you will do that, so this is pretty much going to take some time. So rather than I will run it to show that how it looks in a command window, and I will just continue it. So it will show over here that which alpha is running, how much it progressed, and what is maximum alpha. So it will take a while to run through it because this is a huge range. Maybe it will take a couple of like around 1 hour or something. I tried the last time. So I will just stop it, or maybe I can just pause it, and I can just show you the plots that we will get out of it. So we will get some growth rate plots, something like over here. So we will get the growth rate when we will give the different alpha. For the different alpha, we will see that how the growth rate is changing with the Reynolds number. So for different alpha, we have the different growth rate, and this different alpha become the unstable at different location. So this is only showing the like positive part where the it is unstable. And if we do for the different alpha, like a smaller range, we can get a contour plot, something like this. So we have the contour plot, and this plot is particularly very informative. You can get lots of sense out of it. So this plot is basically known as neutral curve, and where we have the positive value that is showing the unstable region, while the negative one is the stable region. So we can see that there are the region which is the unstable region, which is the positive one, it is bounded by the lines. So those lines, the inner region are unstable, the outer region are stable. So and this start to happen at some particular Reynolds number, which is shown here with the dashed line. So that Reynolds number is known as the critical Reynolds number, which we study for like laminar to turbulent transition. So critical Reynolds number is over here where the neutral curve start, and then it continue downstream, and over the range of the so this is Reynolds number. Critical Reynolds number do not indicate that at this location the transition will happen, but this is the location where the instability begins. So over the time, the instability, if stays unstable, so over the time it saturates and its amplitude may grow or decay. If it keep growing, it will lead to transition. If it decay, it won't lead to transition. So this is very informative. So each of like if you draw a horizontal line, then for each of these alpha, you will get the growth rate curve that we seen over here. Yeah, so this is pretty much about the stability analysis for the incompressible boundary layer, and it will be great if you can try this with the different range of the Reynolds number and alpha to check out whether how this neutral curve look like and what are the range of wave number that can go unstable.